Hello, this is second part of Combinatorics. In the before video, we discussed what is mod, why it is used in competitive programming, and we discussed how to find a power b in O of log b, and what is inverse, why it is used, and how to find factorial and precomputing in O of 1. Let's discuss the next parts. So let's discuss nPr and nCr in this video. What is nPr? For example, there are n values, and we have to permute any three numbers in any order. So for example, if there are 5 values and number of ways of filling these in these 5 indices are, we can select any initially, so 5, and the next one is 4 because we selected one the before index, and we have selected 2, so it is 3 now, and it is 2 and only 1 is left, so 1. So the number of ways arranging this is 5 factorial, and npr indicates that we have to permute r numbers in 3 indices. So initially we can select 5, any one, and next we can select other one because we have already used one, it is 4, and we have used 2 here, so other one is 3. So npr is just 5 into 4 into 3, the number of ways of permuting any 3 numbers. So the first r are the given values to be permuted, and the next n minus r values are the next value into 1 and so on till 1. So here n is equal to 5. 5 into 4 into 3 is npr, and the whole product is 5 factorial, and the product of all these is 2 factorial. For example, if n is 7, 7, 6, 5, 4, 3, 2, 1. So any suffix can be written as a factorial because starting from 1 and ending at that value. So similarly, it is ending with 2 here because n is 3. So it is 2 factorial. So the total is 5 factorial, and the next one is divide by 2 factorial to get this. So 5 factorial divided by 2 factorial. So it is n factorial divided by n minus r factorial. So in this way, the npr can be written in terms of factorials. And now coming to second one, nCr. npr is the number of ways, the total number of ways in which you can arrange. But nCr is the total number of ways without explicitly seeing the order. For example, similarly 5c3, the value of 5p3 is 5 factorial by 2 factorial. To find 5c3 from this, we can arrange the selected 3 numbers in any order. So initially there are 3 indices again. From these 3, because we have to only arrange 3 here, so selecting any is 3, and selecting the other one is 2, and the next number is 1. So we can write a set of 3 numbers from this 5 numbers in 6 orders. So these 6 are same for nCr. So to get the total number of ways, we have to divide by 6 because these 6 are same according to nCr. So the total number of ways is n factorial by n minus r factorial, which is npr, and as these all are same, we are again dividing by r factorial. So this is nCr. As we have seen, 5c3 is less than 5p3 because 5p3 the order also matters, but in 5c3 the order does not matter. So coming to the next one, if we have to find npr mod m, it can be written as n factorial by n minus r factorial. So from the last video we can see that 1 by b can be written as b inverse, so a factorial into b inverse whole mod m, and as we have discussed Fermat's theorem, b inverse mod m can be written as b power mod minus 2. So by binary exponentiation we can find it in O of 31. So we can find the whole npr in O of 31. But can we reduce this further? Can we do directly in O of 1 without any kind of any small iterations even? So for example, a factorial can be written as a into a minus 1 factorial. So if we try to bring here and take a factorial to this, it can be written as 1 by a minus 1 factorial is equal to a into 1 by a factorial. So if we write a minus 1 as j, so it is j, 1 by j factorial is equal to j plus 1 into 1 by j plus 1 factorial. So the main idea here is to reduce the time complexity to find a inverse whole mod m. So in the before video we have seen that to precompute the factorials, we have used the other vector to store factorial of all numbers. Similarly, now the idea is to reduce these and to store in the other vector so that we can find any inverse factorial in of 1. So as we have seen here, inverse factorial of j is dependent on j plus 1. So inverse factorial of j plus 1 will be dependent on j plus 2 and so on. So similarly we can find the maximum value, and we can find it inverse 1 by mx factorial using the Fermat theorem. So after computing this, we can store it in the vector, and now from this one we can just try to multiply j plus 1 into this, as we have found this. Now the multiplication is of 1. So by using this in a loop, we can forwardly store all these in a vector, and we can find in of 1. Let's check the code. So the a power b by Bell exponentiation and the inverse and the factorial. And now coming to inverse factorial. Inverse factorial of maximum value is inverse of factorial of mx. As factorial of mx is already discussed, we want 1 by this, so we want inverse. So inverse also finds a power mod minus 2. So it is just inverse of fact of mx. And now from this, we can check that answer for j depends on j plus 1. So we can start from the last value, which is mx minus 1. So from this we can travel up to 0, and inverse factorial of j is j plus 1 into inverse factorial of j plus 1 and so on. So from this we can store in the inverse factorial vector. And coming to nCr, nCr is n factorial by n minus r factorial into r factorial. We have found this and this all are pre-computed in O of 1. So we can just find factorial of n into inverse factorial of n minus r. So this is factorial of n, and this is inverse factorial of n minus r, the product and multiplied by inverse factorial of r. So this is nCr, and similarly nPr, just inverse factorial of r will not be there. So it is n factorial by n minus r factorial. So it is factorial of n into inverse factorial of n minus r. So if we want to use factorial and inverse factorial vectors in the next part of the code, we can initially call these both functions, which will automatically fill these both vectors, factorial and inverse factorial. And now if we want to verify whether it is working or not, firstly factorial of 6, it is 720, and next nCr of 6 comma 3. So 63 is equal to 6 factorial by 3 factorial into 3 factorial, which is 20. And to verify whether the modular arithmetic is working or not, we can check for very big numbers. So from these both we can understand that nPr divided by nCr is r factorial, right? So these both will be cancelled each other, and the only part left is r factorial, and it will be the numerator. So nPr 100 comma 50 into inverse of nCr 150. So it is indirectly nPr by nCr. So 1 by nCr is inverse of that. So nPr into inverse of nCr. This will be 50 factorial, but we cannot store 50 factorial in the integer. So we are using mod. And similarly, we cannot print it. So we can find factorial of 50, which is also using mod. So these both should be same if they are working. As we check, these both are equal. So in this way, we can find factorials, inverse factorials, powers, and any mathematical operation by using O of 1 or O of 31. Drop a like, comment below. See you in the next one.